Hey guys, hello and welcome or welcome back to my channel. This is Kshitij, and on this channel we talk about robotics, research and academia. This is the second lecture in the TT101 lecture series. So in case if you have missed the first lecture, I'd recommend that you watch it first. The link would be in the I button above, and also the link to the entire playlist of the lecture series TT101 would be in the description. In today's lecture, we are looking into components of a mobile robot. First, we will do a quick recap of what we looked into in the previous lecture, which was an introductory lecture. Then in today's lecture, we're going to look into various types of sensors, various types of intelligence that you could use for planning, various type of actuators, which helps you to act on the decisions you've made based on the information you have sensed, and some primarily control architectures, which are basically methods of sending control commands to a robot to execute certain behaviors. So previously, we looked into what this course is and who this course is for and what you're going to learn. So learning objectives. What is robotics and a robot, type and needs of a robot, and challenges in mobile robotics. In today's lecture, we are looking into components of a mobile robot. So what were some challenges in mobile robotics? Where am I? Where am I going? Can I trust my sensors? How do I go there? And am I doing this alone? So we looked into this in the context of mobile robots in the previous lecture. Now, they could be broadly classified into the sense, plan, and act categories. So where am I? You're trying to sense where you are. Where am I going, and can you trust your sensors for making a plan? So it's a part of your plan or decision making. And how do you go there, and are you doing this alone? Are your criteria for acting upon the plans that you've made based on the information that you've sensed? So first, let's look into various type of sensors. Now, we're not going to go into individual details of each of the sensor types because that would be done in the following lectures. But in today's lecture, we are broadly looking into the various sensor categories. So first up is exteroceptive sensors. These sensors acquire information from the robot's environment, that is, everything that is external to the robot. They could have a varying sensing range, so depending on how much data they could acquire and from where. So if you imagine a sort of sensing radius or a sensing cone around the robot, how big or small this is very relative, but it could be long or short detection range. And some examples include proximity sensors, light intensity sensors, temperature sensors, and so on. Pop quiz for you. What other exteroceptive sensors do you see around you and are very commonly used on a robot? To answer such pop quizzes, you could write in the comment section below. And when answering a pop quiz, always refer to the pop quiz by its number. So for this case, it would be answer to the pop quiz 2.1. The next type of sensor category that we're going to look into is interoceptive or proprioceptive sensors. So for those of you who already know what proprioception is, probably this would sound very intuitive. And for the rest, these are sensors that measure values internal to a robot. These could include things like motor speed, wheel load, joint angles, battery voltage, and so on. Again, another pop quiz. What are some of the most commonly used interoceptive sensors that you see around you? Especially for mobile robots, if you've been playing with them, or some sensors that you could think of. Now, some sensors are active sensors, which means they emit energy into the environment. And then they use that emitted energy, basically the reflected energy, to understand what is around the robot. Think of it like a firefly as you see on the screen. It's glowing, which means it's emitting some photons, which allows it to glow. Now, because it is emitting energy into the environment, it is prone to signal interference within itself and with other sensors that are also emitting energy. So for instance, if you bring your mobile phone really close to your microwave, because they both emit energies, you will start to have signal interference. Or if you have a dual SIM phone, you would have noticed that if you have 4G turned on for both your SIM cards and you allow them to work on flexible bandwidth, that means it could switch between Wi-Fi, 2G, 3G, and 4G. You're going to start to have a lot of signal interference and people are going to have trouble trying to even call you. Also, because it's emitting some sort of energy, sometimes it may even affect the quantity itself that you're trying to measure. Think of some examples of active sensors that we use, and some of them are very common and right in front of you. So go back to the definition of what active sensors are and you'll come up with an answer. Then there are passive sensors, which, as the name sounds, are counterparts for active sensors. And instead of emitting energy into the environment, they measure the ambient energy entering into the sensor. So a quick summary, sensors could be exteroceptive or interoceptive, which some people also call proprioceptive. And there is also an ongoing debate whether proprioceptive is a third category altogether. But for the scope of this lecture, we stick to just two categories. And for exteroceptive sensors, they could further be classified as active or passive, depending on whether they are measuring ambient energy or emitting energy into the environment. So now that we looked into some broad sensor categories, the next up is, once you're done sensing, what happens next? You try to make a plan to try and figure out, okay, well, what is around you, what can and cannot be done. So this calls for planning, or you could also consider this as decision making, or you could also call it intelligence. So there are various forms of intelligence. So let's start with the very naive or the very extreme example on one end, which is no intelligence whatsoever. So if you've played around with drone photography, you might have looked at people, or you have friends who have drones and they do vlogging or they do aerial photography. You would have seen them with a joystick. If not, you might have played with an Xbox. So you would have seen a joystick as shown on the screen at some point in your life. Now, the idea here is that there is a human operator that gives the commands. So you use the keys on the joystick and you're sending commands to the robot. The robot converts the high-level commands to low-level commands. By this, I mean, if you press a button which says go forward, the robot really doesn't know what forward means. It needs to convert it into control commands, which basically could mean send a particular voltage to the motors or manipulate some resistors, etc. And then accordingly, it takes an action. And then after it's done executing, it just waits for your next command. So essentially, the robot is not self-reliant. There is literally no intelligence whatsoever. It's waiting for you to keep sending the commands one after another. And then it just simply executes it. Think of it like a blind, dumb robot. It cannot do much. Another form of a very non-intelligent solution, which could be useful for some cases, for instance, could be preset instructions. So for instance, if there is no, we call it human in the loop. Basically, every step of the way the human is doing something, that becomes a human in the loop. So for example, the previous example with a joystick, there would be a human in the loop sending commands. So even if it's non-intelligent, the human needs to be actively involved to some extent. If that's not an option, what you could do is you could hard code the actions that the robot needs to take. So for instance, you could say go straight for 5 seconds, turn spin in the spot, or turn left for 2 seconds, and so on and so forth. It's like a hard coded trajectory. And that's another way to do it. So basically, even if you have any sensor data on board, like you're seeing something has changed, that would not be accounted for. So you cannot adapt to situations because you've already hard coded everything. So this is not really intelligent, as you could tell. Now comes the buzzwords. I'm sure you might have heard about artificial intelligence by now. Artificial intelligence, you could think about it as the brain. It helps to interpret the sense information, responsible for controlling the sensors, helps act upon the information. So the whole bunch of things depending on how smart and how detailed your programming is. And there's always an unpopular opinion where some people just simplify the definition of AI to just saying it's a bunch of if-then-else statements, where if you don't have an if-then-else condition, then the robot doesn't know what to do. Okay, now we look into machine learning. So machine learning is a type of artificial intelligence. Machine learning allows a machine, as the name suggests, to learn. So it's literal translation from data. Now, this word data is an important keyword. So artificial intelligence and all its forms are data-driven intelligence and learning mechanisms. It allows the machine, the robot, to learn based on the data. So machine learning, typically, when you use these algorithms, you're looking for patterns in the data, and then the machine, or the robot in this case, could learn based on the patterns. And once you have this kind of learning involved, you don't really need to explicitly lay out the entire task instruction. So like last time, we hard coded everything for the robot. Now there isn't much of a need to do it. Or if you really need to do it, there could be like a shared autonomy to some extent, right? So you basically say, okay, unless I interrupt, you do such and such steps, like go forward, turn left, turn right, go forward again, and blah, blah, blah. But then when I interrupt, you listen to me. When I stop interrupting, you go back to whatever the hard-coded thing was. So these kind of intelligent mechanisms and hybrid cooperation with robots are possible. Then again, deep learning. By now, I'm pretty sure you would have come across this term a million times. So deep learning is then a subset of machine learning, where you look into very deep neural networks, which is where it gets its name from. And because they are deep, they have very complex architectures. And it is end-to-end learning. So you throw in a data and out comes a result, but these are usually black box models, which means you really have a problem trying to explain why a robot did a certain thing. So for instance, if a robot decides to, so if you're having a drone, it's hovering at a certain altitude, but then suddenly it decides to go 10 meters higher, and you're using a deep learning framework, it would be very hard to pinpoint exactly which part of the network was the culprit that made the robot decide this. And sometimes if lives are at stake, example, in search and rescue missions, this could be very dangerous. Another problem is it requires lots of data. Because of such a complex architecture, it requires lots of data and heavy computation powers. So normally people use GPUs and TPU accelerations. And it's used heavily in applications like autonomous driving and drone racing. If you have watched The Iron Man, I'm sure you have, you might have heard about Jarvis, which Tony Stark uses to make his life easy in his workshop. Now it's up to you to decide whether that qualifies as an AI, ML, or deep learning. Comment down below and let us know what you think. So based on how well the robot is equipped in terms of the intelligence, whether it's totally non-intelligent robot or it has some sort of intelligence or it's highly intelligent, there could be different levels of autonomy. So you start off with the very lowest level, which is teleoperation or could be hard-coded trajectory. Then you go to the next level, which is guided, also known as learning from demonstration. So this is typically used for humanoid robots to teach them a certain behavior. So imagine I'm standing in front of a robot, which is watching me from a camera, and I do a certain action. Let's say I make a square in the air. And now the robot has to repeat the task, but I'm not going to explain exactly what all commands does it need to give and how should it execute this action and so on. The robot needs to interpret this by itself based on the behavior it has seen me execute. So that's called learning from demonstration. This, of course, gets challenging if you are a human and on the other side is a drone, where the mechanics and dynamics of both the bodies are completely different. Then there is supervised learning, which means whatever data you're feeding the robot has certain labels. So imagine if I'm giving it a bunch of images and I've labeled them that this is a cat, this is a dog, this is a monkey, and so on. And then you give it a new image which does not have a label, and then you want it to figure out, okay, what is this? So this is typically used for classification, but also supervised learning approaches could be useful for robot control. Collaborative could be very useful for industrial applications. So you do part of the work, your robot assists you in taking over the other parts. Typically, the heavy duty lifting is taken off your shoulders, or very repetitive tasks could be taken over by robots and so on. Then comes full autonomy, which of course has various levels of autonomy, but it's typically discussed in terms of fully autonomous robots. Like the robot knows how to maneuver around, how to take off, how to land, how to go back to recharging. So it is basically equipped with various decision-making frameworks to tackle the various scenarios that it's going to be deployed in. One common mistake that I see people make all the time is to confuse the word automation with autonomy. So as a side note, since we're already discussing levels of autonomy, I wanted to make this clear to the learners. So automation is a set of repetitive instructions performed by a robot, often repetitive. So basically, if I tell you do this, and do that, that becomes automation, because then I feed that into a bunch of programming commands, and then off I go, and the robot can keep executing the same set of commands until something in the environment changes where these conditions are not met. Think of it as like, if this, then that. So if this, then do something. If I just say this, and then if that condition is not met, then the robot doesn't know what to do. So this is typical for industrial robots where the tasks are repetitive. For example, pick and place. So pick this, place there, pick this, place there, blah, blah, blah. or every 5 seconds drop a blade to chop something, or every 5 seconds draw the tape to glue something to make a box, etc. But when things don't go according to plan, then there's a buzzer that sounds, and then somebody needs to go there, typically a human, to fix the scenario and then restart the automation process. So then it goes back to just if this then that kind of conditions. Autonomy, on the other hand, is not so much about the process, but it's the state when the robot can operate without explicit instructions. I'm sorry. Basically, things like autonomous driving robots, unmanned robots, where you do border patrolling could be an example, or drone racing or self-driving cars. So there's a different level of autonomy where you don't have to kind of prepare the robot for everything. It kind of learns as it goes, and then the robot can operate without explicit kind of list of commands that it needs to follow. Okay, so now we have looked at sensors, we have looked at intelligence. Next up is actuators, which allow you to take actions. So actuators are essential components for executing the motion. Could be linear, could be rotational, could be a combination. And there are various types. Could be electrical, like AC/DC motors, could be pneumatic, which have pressure chambers, could be hydraulic, which have compressed fluids, could be oil or water-based, and so on. So there are various actuators that allow you to actuate various parts of a robot. Then there are also joints, which are movable components for relative motion between adjacent links. Now, what is a link? Think of your arm. So your upper arm and your lower arm, each of these is a link, and your elbow is a joint connecting these two adjacent links. Okay. So based on the degrees of freedom and how does the joint move, they could be categorized broadly into these 5 categories. So first is a linear joint, where the input and the output joint have collinear axes, and the mobility is along the axes of the joints, of the links. Orthogonal is when the input and the output links are orthogonal to each other, even if the movement of the joint is just translational. Okay, so you displace along a linear axis of the input link, but the output link is positioned such that it's orthogonal to the displacement. Rotational link is a link where the input and output axes of the links are collinear, but the axis of rotation is orthogonal to the collinear axis. Okay. Twisting, again, is where input-output links are collinear, but the axis of joint motion is parallel to them. So then you could twist. And then same way, you have a revolving joint, okay, which, as the name suggests, revolves. All right, so now we've seen sensors, we have talked about various types of intelligence, we have talked about actuators and joints which allow you to send commands to various parts of a robot to make them move. Now, you can't really tell a robot to just, do X. Robot doesn't understand human language. So you need to come up with some control architectures on, what all things does it need to integrate, and how does the final command goes to the corresponding part, which basically brings us to the sense, plan, act loop, which we've been discussing since the beginning. So it has to sense, it has to plan, it has to act, not necessarily in that order, which we're going to see now. So these are called primarily control architectures, and we are going to overview 3 of them in the scope of this lecture. So the first one is the hierarchical control paradigm, where you sense, then you plan, then you act, and then you rinse and repeat. Okay, so this was one of the very early control paradigms. And as I said, so it's you sense the world, then you make a plan of how you want to move. So once you have a plan, and then you execute, which means you take an action, you send control commands to your joints and actuators. Now, when you sense the world, I want to make a point here that the robot makes a cartoon-like model of the world. Now, why cartoon-like? You have to remember, when the sensor senses something, one, it does not sense everything that is around to be sensed, because, as I said, there could be limited sensing range, could be short range, could be long range, but it's not infinite range. Okay. Also, sensors could be noisy. So whether or not you know the noise model, but whatever you're seeing is not accurate. Okay. So that's why we imagine something like a cartoon-like model. So imagine you went to a monument and then you are drawing a painting of that. Even if you make it lifelike, it's not 100% accurate. And then the model contains everything that is for the robot to know. which then again you could imagine makes it very slow to make any decision whatsoever, because there are much more information to be processed than what is actually required. So this was the drawback of this architecture. Okay. Now then people came up with this idea. So that was a lot of deliberation going on in the previous architecture, right? So you sense a lot of things, then you make a lot of plans, and then you figure out, okay, what action do I take? And then you rinse and repeat. So there was planning going on, which means you were deliberating. Then came this architecture called the reactive control, which, as the name suggests, is reactive, not deliberative, which means planning is no longer involved. You sense something, you immediately act. Think of it like you touch a hot object, you immediately pull your hand back. You're not going to think, do I pull my hand back this way or that way, or should I go around in circle or whatever? There's no planning required. You immediately react to it. Okay. So planning goes out of the picture. It's a fast execution because you sense and you act. And every sense-act coupling is known as a behavior, which means there could be multiple of these couplings and hence multiple behaviors. So for example, you have a behavior of what to do when you touch something hot, when you touch something cold, when you touch something fragile, etc., etc. So there are multiple behaviors, which means depending on what stimulus you get while sensing, you have a plan, not a plan, an action. So you don't need to plan anything, okay? So you have behaviors, and your final behavior could be a combination of a lot of these behaviors as well. Then comes a hybrid, which is an obvious question. So there were pros and cons of both the past models. So in the 1990s, we came up with this idea of picking up the best of both of them. So the way this works is at the bottom, you could see there is the sense act reactive kind of control paradigm, but there's also a planner which draws information from both what you've sensed and what actions you have decided, your behaviors. Okay, so there is a two-way communication going on with the underlying base being a reactive paradigm. So the way this works is you plan, which means you deliberate first, and you try and decompose the task, divide and conquer. So once you have decomposed the task, then you select behaviors or actions for each subtask. So as I was saying, what happens if you send something hot, something cold, something fragile, etc., etc. So you kind of allocate behaviors for each of the subtasks, then execute as per the reactive paradigm. So out of these three paradigms, I'm sure there are a lot of pros and cons for each of them. And this is not an exhaustive list by any means. Can you think of some other paradigms which are more prominent in today's times? Comment down below and let us know. All right. So this was an overview of the various components of a mobile robot, primarily spanning sensors, planners, and actuators for taking actions. In the next video, we're going to look into various types of sensors and what they can and cannot sense. So we're going to start going deep dive into each of these components in the following lectures. These lectures are aimed for absolute beginners who are learning robotics for the first time. So we are interested in covering more of a breadth rather than the depth for each of the pillars. And you need to make sure that you're watching the videos in a sequence. Otherwise, the chronology may or may not make much sense in your head. In case if you missed the videos, the next video would always have the link to the previous video in the I button above, and also the description for the entire playlist in the description box below. So you could click on either link and catch up if you missed any. I hope you're liking this video, and be sure to like, share, and subscribe to my channel so that you're notified as soon as the next video goes live. See you next time in the next lecture. Take care and have a nice day.